everyone, myself is Divya Bahel, Assistant Professor in Chemical Engineering Department at LJ Institute of Engineering and Technology. The subject that I am going to take is petroleum refining and petrochemicals. So, moving with the lecture, now in your first chapter, that is basics of petroleum industry, okay, the next topic is about crude assay analysis. Okay, we studied about crude assay analysis in the last lecture, and now moving forward, distillation characteristics. Now we have to go into detail about distillation characteristics. See, distillation characteristics is one of the major important part which is done as a part of crude assay analysis. Okay, crude assay analysis is nothing but evaluation of certain physical properties. Now, in refinery, the distillation is the major separation process. Okay, so you need to know the boiling range, that is from top product to the bottom product, the boiling range in which you will get various fractions. So crude assay analysis has certain characteristics. Okay, this test, that is ASTM, distillation, EFV and true boiling point, these tests are done to know about the boiling range of your crude fraction. Okay, now this is done as a major part of crude assay analysis. Now these tests are known as distillation characteristics. See, why characteristics? Okay, distillation works on the basis of applying heat and because of the volatility difference. So your prime object is to know about the boiling range of your components. So moving forward with this test, okay. Now, starting with the true boiling point analysis. From name itself, you can have an idea that this type of analysis gives you actual boiling point. Okay, it gives you the most accurate result about the distillation range. So, now why this process is called as true boiling point analysis? See, in distillation, how your crude is refined. Okay, important additions into the distillation tower is that it is a fractionation unit. Okay, various stages are there, plates are there. A plate column is what is fractionation column. Okay, and besides that, reflux condition is also there. So we have two criteria here, that number of stages are there and reflux condition is also there. Now it is important to note here that how purity of your component increases. See, it is totally because of reflux. As you increase the reflux, what does reflux do actually? It is having more and more contact between liquid and vapor phase. Now, revising the distillation concept. Okay, see, distillation is an example of equimolar counter diffusion. Okay, your liquid and vapor phase come in contact with each other and there is a transfer of molecules. Okay, from liquid to vapor phase, low boiling and heavy boiling components transfer into each other. Okay, now when can this be achieved? When you increase the reflux. So what this analysis does is, it gives you more number of stages and reflux condition also. So let's have a look over it. Now in lab, how you will conduct the experiment. Okay, you can see the fractionation column. Okay, here it is a pack type. Okay, the packing is of glass beads. So what this glass beads does is, it provides maximum contact between vapor and liquid phase. The number 2 suggests the boiling flask. Okay, you take your sample in the boiling flask. The amount of sample will be 200 to 500 ml and you heat it. Now as heating takes place, your more volatile component, okay, note here, the component which is very volatile, first it will vaporize. Okay, now as the vapors rise upwards, you are now introducing reflux also. Okay, now because of the more contact, your reflux will, because of the more contact with the reflux, now your vapor which is pure, okay, it is high in component in the more volatile. Okay, those will travel with condense and is collected in the collecting cylinder. Okay, this way your process of distillation is done here. Now, because it is accurate, it is called as true boiling point analysis. Okay, now how this experiment is done, okay, how this distillation is carried out. So the firstly under atmospheric condition. Okay, now 1% is distilled every 2 minutes. You can obviously know from it, initially when you are subjecting your sample to heat, more volatile components will vaporize. Okay, so the distillation would be fast. At every 2 minutes you will get 1% distilled. Okay, now that was under atmospheric pressure. Now as your more volatile component get vaporized, okay, now the remaining in the liquid are the heavy fraction. What are heavy fractions? Which are very high boiling point or are less volatile. Okay. Now to distillate them, okay, second we are doing is vacuum, under vacuum. Okay, now why under vacuum? To prevent the cracking process and to reduce the boiling point. Now as the remaining liquid in my sample is heavy fractions, okay, which have very high boiling point, so to prevent the cracking. Now when does cracking happen? For thermally sensitive materials, okay, they are prone to cracking. So what happens is, it is nothing but a thermal degradation. Your original molecule will crack into other fractions. Now we don't want that, okay. So what we are doing is, we are trying to decrease the boiling point. Now it must be known, okay, as a revision of your distillation topics, boiling point is function of total pressure. As you decrease the pressure, your boiling point will also reduce. And so secondly, you are conducting this test under vacuum. And what is the pressure? At 440 mmHg. Now you can see the distillation rate has been reduced. See, now at every 3 to 5 minutes, only 1% is distilled. So what we do is, in this process, we collected data of pressure versus temperature plot. Okay, we collect the data of temperature versus percent distilled to get a TBP curve. So now for the laboratory test also, at least 10 to 15 trays are used. Okay, now equivalent to 10 to 15 trays, you have your packed tower, and with suitable reflux condition, this test is carried out, and so you get the accurate results. Okay, see, because of this, there is very less mixing between more volatile and less volatile component. Okay, because of reflux and number of stages which is done so as to increase the contact between vapor and liquid, what you are trying to achieve here is, you are trying to make sure that mixing between more volatile and less volatile components is very less. So the top product, the distillate you will get, which is of the top product and which are very more volatile, okay, it would be having very less amount of heavy components. So you will get accurate results of boiling point range. Now the next here is ASTM distillation. What is ASTM? It is abbreviated as American Society for Testing and Materialization. Okay. So under that category, we have a test for distillation. It is a very simplest form of distillation, the one you carry out in laboratory. Okay. So the arrangement is, see, you are heating again your distillation flask. A sample is collected, put in there. It is heated. The high volatile components vaporizes. The vapors travel upwards and then it is condensed and it is collected in a cylinder. Okay. The difference between TBP and ASTM is, now you are not providing a fractionating tower. Okay. You are not providing a packing material. So less contact between vapor and liquid is there, plus you are not providing a reflux condition. Okay. Well, actually what is reflux? As a revision of your distillation again, what you do is, the more volatile component which vaporizes, travels, it is condensed and it is liquefied. Okay. And what is reflux is, you take a part of that distilled liquid and you transfer back into the fractionating column. So that is reflux. Okay. Now here no reflux is there. So of course here reflux condition is not there, neither are you providing stages. Okay. It is a simple arrangement. Okay, now this distillation is used with fractions having short range of boiling point. Okay. Again, no reflux and stages. You can see the fractionating column which is located between condenser and the flask. Okay, there is no stages, neither is the packing. Again, it's the simplest form of distillation. Now that was about your ASTM distillation. The third type of distillation you do is the equilibrium flash vaporization. Now the arrangement is this way. So what actually happens here is, what you are doing is, first of all, the feed. Okay, you have taken a sample. The first process you are doing is, you are preheating it. Okay, you are heating it. Now because of heating, what you are doing, you are increasing its enthalpy and you are increasing its pressure. Okay, because of increase in temperature, pressure will also increase. Now this increased pressure feed is now sent through a pressure reducing valve. Okay, now its pressure is reduced. Now because of reduction in pressure, its boiling point will decrease. So what happens? It is a part now when this reduced pressure feed is introduced into a column, then it is partially vaporized. Okay, partially vaporized means a part of liquid. It is called as flashing. Okay, this liquid will enter the column in form of flash. Part of it will be vaporized and part of it will be liquid. See, the pressure reducing valve reduces the pressure. Okay. Now, a throttle valve pressure reduces, so flashing occurs. What it reduces the pressure. Now, how this method is different? See, in the column now, vapor and liquid will be in equilibrium. Okay, now again revising the concept of distillation. What is your driving force? It is difference between your existing condition and the equilibrium condition. Now already equilibrium is there between vapor and liquid. As it enters the column, vapor and liquid comes into an equilibrium condition. Now it means as equilibrium is achieved, now no more further separation will take place. Okay. So vapor and liquid are in equilibrium, hence no more further separation. So this was your equilibrium flash vaporization. Okay. As I told here, no separation can take place. It means in vapor phase, you can also have your less volatile components. So here you can say mixing is there. Okay. Same is the case in ASTM distillation. Now let's compare them. Okay. Moving before comparing, some of the important terms which you need to know. What is IBP and FBP? IBP, it is called as initial boiling point. Okay. It is the minimum temperature at which first drop of your distillate appears. Okay. As your more volatile component vaporizes, it is distilled and you get your first drop of your distillate. So what is that first drop? It is because it is a fraction of the most volatile component present in your sample. So of course that is the initial boiling point. More the volatile component, less would be the initial boiling point. Okay, you are getting that distillate at very less temperature. It suggests that your component is very volatile. It vaporizes very early. And the final boiling point is, it is the maximum temperature at which your highest boiling compound evaporates. Okay, it is generally measured. How it is measured is, in your flask at the end you have the residue. Okay, the temperature of that residue would be maximum and that is your final boiling point. Now comparison between these three. Okay, the main aim of this analysis was to have a plot of temperature versus volume distilled. Okay, so you can see the initial boiling point, the TA and TB. What is TA? TA is your initial boiling point. TB is your final boiling point. So you can see that for TB, okay, for true boiling point analysis, your TA, that is initial boiling point, is minimum, whereas TB, maximum boiling point, is maximum. Okay, final boiling point is maximum. So why minimum? Okay, why least of all? Because it gives you pure accurate results. Okay, mixing is very less between less volatile and more volatile. So in initial boiling point, the distillate which you collected, that are mostly free, or that is almost pure composition of more volatile component which vaporizes very early. Hence at very less temperature they are vaporizing. Okay, and so the temperature is minimum for the case of true boiling, and similarly for the final boiling point. Next is ASTM. Okay, and final is the EFV, equilibrium flash vaporization. As I told you, because equilibrium condition is achieved, hence no more driving force exists. So it gives you hence because of that it has the most mixing between the more volatile and less volatile components. So this was about your comparison between ASTM, EFV and TBP analysis, which gives you distillation characteristics. That is the most important, that is boiling point range. Okay, because of least mixing you can see TBP gives you high final boiling point and lowest IBP. So you can see comparison for final boiling point. The final boiling point in TBP analysis is more than ASTM, is more than EFV. Whereas for initial boiling point, okay, your TBP gives the minimum value, ASTM followed by EFV. Okay. Now this was about your analysis. Now moving further. Okay. Now our motive is to know the average boiling point. Okay. In distillation column, your fractions are taken out as a cut. Okay, within such temperature range. Suppose take any example. For example, gasoline. For between 30 to 120 or suppose 30 degrees Celsius for between 120 degrees Celsius. The cut I am getting between that range, that cut is called as gasoline. Okay. So in fractions of various boiling points, you get fractions of your components from crude. Okay. So now we need to know the average boiling point of those fractions. Okay. So let's have a look. Okay. It's a basic now involved. Suppose I'm carrying out an example taking 100 ml of sample. If I'm getting 10 ml of distillate from that sample, then that is called as 10 volume percent cut. Similarly, when I get 20 ml, further 20 ml, then that is called as 20 volume percent cut. Same when I'm considering my readings in gram. Okay. Now for 100 gram sample, if I'm getting 10 gram of distillate, it means that is 10 weight percent cut. Okay. So, and similarly in case of mole fraction also you can see. Okay. For 100 mole of sample, if I am getting 10 mole of my distillate, that is 0.1 mole fraction. Now, see VATA. What is VATA? Suppose 10 ml distillate is my A reading. Okay. That is my A quantity. So, that is 10 ml is what? VA. Volume of that cut of distillate. A is my cut. That is 10 ml. The corresponding temperature of that cut is TA. So, now moving forward, how I am going to represent it? So, the various average boiling points are described on the basis of such quantities. Moving forward, volume average boiling point. What is volume average boiling point? It is average of temperature at different volume percent cuts, like the temperature at 10% volume cut. From here you can see TA. Now here what would be my TA? It would be T 10%. Temperature of 10 volume percent cut. Okay. Similarly at 30%, 50% up to 90%. So average, so therefore divide by 5. So that is my volume average boiling point. Now where this is used, for which physical properties do we need to know this? The physical properties are for viscosity, specific gravity. Okay. The viscosity of that fraction. Okay. See, viscosity is also, density is also function of temperature. Okay. So for that reason, to suggest, to define the viscosity of that fraction. Now at every temperature range the viscosity would be different, but for a whole fraction we are taking into account boiling point. So for physical properties like viscosity, specific gravity. What is specific gravity? It is a form of density. Okay, density of fuel divided by density of water. So that way, for that physical property it is used. Similarly, weight average boiling point. Now instead of volume percent, I am taking weight percent. It is used to know critical temperature. Similarly, molar average boiling point. Now instead of 10% volume cut, I am taking my mole fraction. Now here, how instead of average, what is that? Temperature of that mole fraction upon the total moles of your components. It is used to define characterization factor. Now, other forms are mean average boiling point and cubic average boiling point. For mean average, it is mean of initial boiling point and final boiling point. So, we find IBP and FBP using other three analysis like ASTM.EFV, TBP. So, they are doing the mean of those two. You get your mean average boiling point. Now, for which physical property? For specific heat. Similarly, you have cubic average boiling point. Okay. Now, volume of A cut into temperature of A cut, it's cube root, and this way for different cut it is done. Now that is used for viscosity. So this was for today's lecture. So thank you.